as we get further into this chapter, what you're going to find is a lot of the information is going to be very similar. So, kind of why I was curious about the quiz, how it went, because you're going to feel like you're doing a lot of the same things, just they're called different. Who should we go with? Sure, Poyer has. Yeah. If you had to briefly explain how to do the first derivative test, how do you do the first derivative test?
Defines critical numbers.
Critical numbers is when first derivative is equal to 0 or undefined. Yep. What do you do with those?
Yeah, plug in this like a line graph, I guess,
Put them on a number line.
and then you find like the slopes between those points.
So you're going to test interior numbers in the first derivative.
Yes.
Okay. Now, using your critical thinking skills as a calc student, if you had to guess how to do the second derivative test, do you think you could guess that?
I guess.
I'm trying to lead you. Oh, do you want somebody else to guess?
I think Neil likes to guess.
Okay, Neil. I thought this was going to be an obvious answer.
You take the two derivatives instead of a one,
Second derivative equal to 0 or undefined.
and then find critical numbers, put on the number line, and find slopes.
Okay, you meant correct. Said it badly. Second derivative equal to 0 or undefined. Those are going to be called pips instead of critical numbers. I'll explain pips. You're going to put your pips on a number line, and then you're going to test the interior numbers in the second derivative. It's the exact same thing. So this section theoretically should go really fast. Now, the only difference is you learning the new terminology. The actual second derivative test is identical to the first derivative test. Every part of it is exactly the same. Now, you'll notice in your notes that there's like 3 pages of writing here. I don't want to overload you with information because it's the exact same thing as the first derivative test. Now, what a lot of this information on these pages is for is telling you about the second derivative. Now, we've kind of already talked about it and done it, but we've never like defined these things, probably. Second derivative refers to concavity. And concavity is just another word for curvature. So if you have a positive concavity, then that means your function would be curving upwards. That's not a marker. So I want a different color. A positive concavity means the second derivative is positive. Now, the actual definition of positive concavity is that your slopes are increasing. So that's what this picture was intended to be. If you were to draw some slopes, you will notice that the slope answers were getting bigger. So there's different ways to find or define concavity. Now, the one thing that is sort of strange to me that I have never really covered or gone over in any class I've taken is we very specifically have like numbers that represent slope, right? Like you guys know what a slope of 1 looks like, you know what a slope of a half looks like. The numbers represent something. Well, in the second derivative, the numbers represent something as well, but it's usually not something that you can really picture. So a concavity of 1, I have no idea what it looks like. I mean, like, might look like that. I don't know how a concavity of 2 looks like as well either. The only thing that I've ever gotten out of it is that the larger the number, the more that it curves, right? So like a concavity of 10 means that it's going to curve up sharper than a concavity of 1, which would be wider. The only thing that really seems that most people really ever seem to care about with second derivative is if it's positive or negative. Not sure why, just that's all I've ever run into. I'm sure that there is some field that those numbers represent something and get used for something a lot more. Like, I know technically second derivative could be acceleration. And so acceleration, obviously, we use differently as well. But I'm sure concavity gets used in some fields. I've just never run into it. And I didn't write this up here yet, but I'm assuming you could have figured that out. And if you draw the slopes are getting smaller. It's kind of a weird word when you're drawing slopes. The number is getting smaller. So this is like a slope of 0, slope of -1, slope of -2. So the number is going farther downwards. Okay. Yep, we got that. Let's try to do this one semi together. Given f of x equals 1/3 x cubed minus x, determine the open intervals on which the graph is concave upward or downward. State the point of inflection. Explain how you know. I'm assuming most of you will read this sentence and have a big question mark in the middle of your head. Hopefully. Because I don't think I've ever talked about an inflection point. Unless you read ahead, and then in that case you probably already know. Has anybody in here ever done inflection points? Okay, then what I'm going to do is I am going to, we'll do that for now. And I will show you what a point of inflection is. Okay, so Hannah, what should I do to try to figure out where it's concave up or down?
Take the first derivative and then the second derivative.
Perfect. Go right to the second derivative, which you're correct. We can't go right to it. So we've got 3 times 1/3 minus 1, and my second derivative is 2x. Okay. Maria?
You could do another number line. No, wait, find the 0.
No, wait. Like which?
Like, find the 0 of the derivative.
Okay.
Which would just be 0.
Yeah. Honestly, it wouldn't have been terrible if you wrote a number line to start with, but okay. So this is the zeros and the undefineds, just because it's an extremely simple equation. So we only have one. This is not going to be called a critical number. We obviously did the exact same thing. It's just not called a critical number because it's not in the first derivative. In your notes, I noticed that it was called the critical numbers of f prime, which I don't ever want to hear you say because I feel like that's really going to confuse you. So these are called pips. Partially, I like it because it's kind of fun to say. Pips are possible inflection points. And guaranteed you will never see pip as a term on an AP test. These don't really have names, so. Okay, so possible inflection points. And then, correct, we do the number line, put 0 on there, and this doesn't have any kind of domain restrictions, it's just forever. And Jack?
You plug in number to the left and number to the right of 0 into the second derivative.
Perfect. Plug any kind of a test number into the second derivative. So I guess this second derivative is awfully easy, so it really doesn't matter what number we pick. So 2 times -1 is -2, which is a negative answer. 2 times 1 is 2, which is a positive answer. And then, I don't know if anybody will know this. What do these plus and minus signs stand for then? It does not stand for increasing or decreasing anymore. Oh, yeah. What were you going to say, Poya?
Of the concavity of like the function is kind of like increasing or decreasing.
Okay.
Or maybe if you look at it from like a first derivative graph. That's
Correct.
like the point of-
So a negative symbol is concave down. So the concavity, usually you phrase it as concave up or concave down. Now this number right here, the 0, it's no longer a critical number, and it's no longer going to be a relative max or min. This 0 is called a possible inflection point, right? Like we already kind of wrote that down. An inflection point is going to be a point on your function where your function changes between positive and negative concavity. So then we're going to look at this. First thing we're going to do is find out if it's a point, which it is. So if I plug 0 in the original function, I get 0, 0. So it is a point. Ooh, that kind of looks like a little face emoji. That was a pretty good drawing on my part. It's a point, and it changes concavity before and after. It doesn't matter if it goes from negative to positive or positive to negative. Because it changes concavity, downside to these calc notes is it's super hard for me to write small on this tablet. So I don't know if you guys can read that or not. I'm trying my best, but because the concavity alternates before and after that point, so it's a possible inflection point, and if you find out that the concavity alternates before and after, then it is an inflection point. So when we do the second derivative equal to 0 and undefined, and we call them possible inflection points, there's only 2 things that could make it not an inflection point. One, it's not an actual point, like it might be on a vertical asymptote or something. So in that case, it's not a point, it can't be an inflection point. 2, the concavity doesn't alternate before and after, and you definitely will have functions where that happens. It doesn't have to. So it's a relatively simple definition, but still, you kind of have to follow the rules of it. It's very similar to relative max and min, where relative max and min is when increasing and decreasing alternated before and after. But this is just a single thing. I don't know if you can picture it in your head or not. Do you guys know what an inflection point will look like? Okay. I think there's one on the next page. It's so hard to draw it. Oh, yeah, there is. There's a bunch. It's really hard to draw it nicely. So on its own, the definition is relatively simple. It's where your function changes between positive and negative concavity. What that's going to look like is that's a highlighter. It's going to be the point in the middle between curves. So this is positive concavity, negative concavity. And the inflection point would be in the middle of it. And it generally looks the same all over the place. The main difference is the concavity before and after could be sharper, like this one you can see actual curves, where you get to the third picture, and the third picture is still actually the exact same thing. This is still concave up, this is still concave down, but the concavity is lesser, so it's kind of not as steep. Whoop. Now, it's not going to be huge for you to be able to spot them with your eye. I mean, I think some of you naturally can just look at a graph and figure out where it's changing from curving. I know I've had some students in the past have a really hard time just looking at a picture and being able to find that. Now, if that's the case, that's fine. I don't recall in an AP test you ever needing to identify it from a picture. Okay, now there's tons of words that say what an inflection point is. I kind of wanted to show it to you in a problem because that's traditionally going to be easier for you to follow what it'll look like. Everything that's set up here is fine, but when I read through it, it felt confusing to me, and so I knew it would feel confusing to you. So I kind of wanted to explain it differently. If nothing, you guys have multiple ways of having an inflection point explained to you. Now here's some pictures. First one is sort of the most obvious because you've got downwards curve, upwards curve, inflection point in the middle. Second one is weird, even though it's still an inflection point. It's not smooth, but it doesn't have to be. So you've got upwards curve, so positive concavity, downwards curve, negative concavity, and you have a point directly in between them. I think I mentioned this the other day. Do you guys want me to draw what positive and negative concavity would look like on a graph? Would that be helpful to see that? I don't know where you're going to write this. Positive concavity will look like a U, but it doesn't have to be an entire U shape. It can also be any part of the U. So frequently you're going to see just that part of it or just that part of it. As long as the piece you're looking at is part of a U shape. I'm hoping somebody by now has figured out this super obvious way to tell between positive concavity and negative concavity. Why is a U shape super helpful and easy? Positive concavity is known as concave up, U up. If you have a upside down U, that would be negative concavity or down. And the same thing, any part of a downwards U shape. And like I said, I know for some people this just feels supernatural to be able to look at a picture and just it's easy for them to identify where it's curving up, curving down. Some people, it just like never clicks. And that's partially okay. You don't necessarily need to be able to identify it from looking. You'll need to be able to draw it on your own, but that's actually easier. Okay, so here's what I was talking about. This is obviously a U shape, so that's upwards. This piece right here, oh God, what's that going to be considered? Down, because it's part of an upside down U. This is part of a right side up U, so it's up. Those are going to be the only two shapes you'll run into. U or upside down U. And you can pick any part of the U figurine to make curving upwards. Oh, do you need me to go over why this one's not an inflection point? I know we got kind of sidetracked in the middle of this. Which curvature is that? Positive, it is upwards. It makes part of a U. What curvature is this? Also positive because it makes part of a U. So it does not alternate concavity. That's why it's not an inflection point. And then the bottom one I thought would be as obvious as ever. Like, I don't think I need to explain it. Like, there's not an actual point in between the two pieces, so it can't be an inflection point. It alternates concavity, but there's no point there, so. What time is it? 9 o'clock. Perfect. Should we do one together and then have you try one on your own? Okay, let's do example 3 together. Obviously you've got some writing on the right-hand side of the box of yours. I erased it because to me it actually made it harder to do the problem. Like, I don't like when it has stuff there for you to fill out because. What? Okay. My phone did not understand it. Oh, yes. Everybody in here probably is going to write their format a little bit differently. So I don't like when it's pre-filled out for you that you have to follow that. Okay, first derivative, 4x cubed minus 12x squared. Second derivative, 12x squared minus 24x. Emma? No? What would you do next? Or do you want me to call on somebody else?
Would you set it equal to 0?
Oh.
And find the pip?
Yeah, yep, the pips. Did you find them? Or are you working on that?
No, I haven't found
Okay,
it.
why don't you find them? I'll wait to have you tell me what to do then.
Okay, so, take a 12x out.
Good. Factor it out, yep.
So then it would be x minus 2. So then one x would be x equals 0, and the other one would be x equals 2.
Perfect. Nice job. Oh, I screwed that up. Do you want to pick the next person? Okay, Magdalene.
Okay, now test -1, 1, and 3 into the second derivative.
Okay. Here's a tip. Use the factored one. Because we are generally only trying to figure out positive and negative, we don't need to find an actual number answer. Using the factored one is usually a lot easier to figure out positive and negative answers. So plugging -1 in would make this -12 times -3, which would be positive. I think you said -1, 1, and 3.
Yeah.
Okay. 12 times -1 would be -12. Okay, then 3. Three would make 36 times 1, so that's positive. Okay, so I got the answers I needed out of that. Caden? First, tell Jack to get off the phone. There you go. I'll let you take it over from here. What should we do next?
So the negative
Okay, I will label them.
And then the positive is concave.
Perfect.
Yeah, I don't know what else to do.
Okay, so you were done there.
Yeah.
Okay,
That's all I got.
okay, Luke? Do you want to back up Caden?
Um,
He didn't know where to go from here. I mean, also don't feel bad. You answered half of it. Like,
oh, just to plug in
good.
the pips back to the regular equation.
Okay, so the pip of 0 would give us 0. That was easy, okay. The pip of 2, oh God, 16 minus 32, think. Okay, good. What do I do with those? Now that we found that they're actual points, you're basically there. There's just one tiny thing left.
You can label it, they are inflection points.
How come? How do we know? But you're right.
Because they change concavity.
Perfect. So this is an inflection point because concavity went from positive to negative. This is an inflection point. I suppose I should say concavity. Concavity. Concavity went from negative to positive. Good. Now, as we go forward, you'll probably start to see. I know I mentioned towards the end of the hour yesterday, pointing to the backboard, and I said that's kind of our tentative schedule for the rest of the try. You'll notice that on the test, I split up the test into 2 days. And it's not because there's a lot of problems. It's because these problems take forever. So by the time you get to the end of the chapter, I'm going to give you a function, and you're going to have to do the first derivative test and the second derivative test from each function and be able to find tons of things. And so it takes forever. Like we just did this with second derivative. You'd have to do the whole thing with first derivative as well. And it gets to be pretty slow. And correcting these is, you don't care about the correcting, but for me, I hate this chapter. Correcting this is just a nightmare for me because I have to follow every little step that you do everywhere to see if you made a mistake and where. And then I have to try to determine what part of the problem you got correct. And it can take a really long time. Okay. Try number 4. Just do concavity and if there's inflection points. Bless you. I'm trying to let you do this on your own, but I want to get the answer put up there for us to be able to move along quicker. And then I can certainly talk about it or answer questions after. I keep forgetting to write the number on the top so that I have more room to write.
Isn't that on a closed interval though?
It is. Oh, Thanks. Good call. Oh, I wrote F. It's G. Sine of pi halves is 1. Three pi halves is -1. Okay. Now, I don't know where you are in the problem, or if you have questions on something I wrote up there. Yeah.
So say we had another like possible inflection point, and for some reason it didn't change, it went like negative and negative.
Yep.
Where then, what do we put if that happens?
Nothing.
Do we just nothing?
Yeah. So it's called a possible inflection point to start with. I should have written that up there. And then we basically just test if it is. So it doesn't have to be. It's kind of like how some of our points before weren't relative maxes or weren't relative mins, they were just nothing. So they can be nothing. They're just possible ones. Yeah.
Where did you plug in the pi to find the inflection point?
Original function. So actual points come from the original function. And then were you guys okay with why I just used pi and I didn't use 0 or 2 pi? So you only want possible inflection points or possible critical numbers in between the endpoints if there is some. The endpoints can't be curving up or curving down. They're just a single point. And so like when I give the final answer, like for concave down intervals, it's in between the endpoints. Okay, one last problem, which I know today's a ton of info. What I'm trying to do is I'm trying to get a lot of this info done so that when we don't have school on Friday, you guys can use a lot of that time, including Flex Tuesday, to do homework on 5.5. If the faster we can get done, the more time we have to review / take the test early. And for a lot of you, I'm sure that's going to be helpful because you probably have a whole bunch of tests that Thursday, Friday. Because most of the teachers, I think, like you give them Thursday and Friday. And if we can get done slightly early, I think that's beneficial for you, but I'm not going to push it. So if things are going hard, we'll just keep taking our time. So the next one I wanted to try was 6. Using a calculator, find the value of x at which the graph of y equals e to the x squared changes concavity. So hopefully you have a calculator with. Desmos would work if you have Desmos. So e to the x, x squared. I wanted to clear everything first. E to the x times x squared. And I'll kind of take it step by step with you guys. I guess first thing, does everybody have this graph? We should definitely start with that. No. Did you figure out where? Okay. Hit zoom 6. Okay. Any thoughts on how many flex points this has to start with? Or should we zoom in? One is semi-obvious, not semi. Like this spot right here should be kind of obvious-ish, okay? Because the right-hand side is clearly curving upwards, so that's the only like really easy part to identify. I kind of think we should zoom in first because this portion here in the middle, number one, it's super pixely, so it's kind of hard to actually see what's going on. And depending on your calculator, this can look even worse. So I feel like we should squish the y values down. So it doesn't even go into the negatives hardly at all. So let's just say -2. And then the height, it shoots up high at the end, but I didn't care about that part. So I feel like let's just go -2 to 3 or 2 to 2 or something. See if that helps. That definitely helps. So now it's easier to see curves. If I want, the right-hand side is totally useless because that's all blank. Why don't I make the max go to like 2? There. So stretching it out some can help you look at the curves better. So this one's going to have 2 inflection points. I don't think I can write on here. No, I can't. One inflection point is right here-ish because it's curving downwards and then it curves upwards. So I'd say there's one right about there. And then there's going to be one right about here because this is curving upwards and this is curving downwards. I mean, it looks like a nice smooth curve, smooth line because it is, but this is curving upwards and then it curves downwards. Now here's the hard part of the problem. If you go read the piece of paper, it says find where they are. And we can't guess because we're using a calculator. So how do we find exactly where they are?
You graph like the second derivative line and go to x's and the x intercepts.
Okay, we could do that. Should we try that? Do you guys remember how to do that? I want you to try to see if you can type the second derivative in first. I mean, that sounds like a great plan to me, so. Because that's basically exactly what we've been doing. Possible inflection points where second derivative is equal to 0 are undefined. Fair warning, your calculator is going to graph real slow. To help you out, you don't care about the first derivative. You can turn it off. Click on the equal sign and it won't graph it. Now, I've actually never tried it. I wonder if we could have done d dx of d dx, like do the second derivative or do the derivative notation twice. Did it work? Perfect. Cool. I should try that next time. How do I get answers from this? Or should I wait a little bit for you guys to get this graph up there? I don't know how long it's taking you, or I don't know how long it's taking to graph. Probably a while.
It's good now.
Okay. Tyler? Thoughts on how we actually find the answers from using that black graph? So the black one stands for the second derivative. Do you remember how we found pips in the second derivative? Pips are possible inflection points. And we kind of just looked at the picture to figure out which ones are inflection points. So how do we, what was the first thing we did with the second derivative test?
Well, we made it equal to 0.
Good. Figured out where the second derivative was equal to 0 or undefined. And so from our picture, we want to find where it's equal to 0. This one right here is really easy to spot because it's a steep line. But I'm pretty sure there's a 0 somewhere here too. And it's okay if you can't spot it on your own. I'm going to use the calculator to find the 0, number 2. Make sure you have it on the correct line. So I'm going to move way over here because I have no idea where it crosses. And I'm going to hit enter. And I'm going to move way over here because I know it's below the line down here. And when it says guess, it doesn't have to be super accurate. Oh, okay, way over there. It's a good thing I put the right bound way over there. So I guess negative 3.1. 3.41. That one really screwed me up because I was thinking pi in my head. 3.41, not 1.4. Okay, so there's one critical number. No. Oh, said that totally bad. My fault. This is one of the possible inflection points. How do we find the y value of this x?
Press the up arrow.
We can hit the up arrow. Sure. Oh, actually, you know what? That's actually super nice and easy. I was going to tell you to trace, but we don't need to because it's already at the exact same x spot. That's convenient. Good call. Okay, so this would be the point. This is the inflection point. Are you asking a question, Jack, or just?
No.
Okay. So then to find the second inflection point, I need to find the other 0, which was way more obvious on the black line over here. And it is going to be negative 0.58, 5787. That's the point. Now, the reason I picked this question over the previous one, if you look at the previous one in the notes, excuse me, The previous question just said kind of eyeball and estimate where the inflection point is. I believe it said something like that. And that absolutely we could have done on this problem as well, but I wanted to make sure to go through the steps and for you guys on how to find the exact inflection point, because I feel like that's a more realistic question on the AP test. You'll never be asked to estimate an inflection point. That was a good catch.
Did you see that?
Yes, I did. It was a very good catch. That's why I get bottles with lids.
I can't put a lid on this one.
No, I know. I just don't trust myself. I've got a computer over here. I guarantee I'll. Okay, I guess I'll stop here. That was pretty much solid all throughout the hour. Having said that, I pushed to get a lot done today so that tomorrow we'll have very little and you'll have a lot of time to work in class.